it is not, in the sense that it is very different from the point of view of physics. Completely different topic. But technically, the detectors that are used to search on the fundamental decay are similar, sometimes identical or very similar to the one used for technical search. So it is a very different topic from the scientific point of view, but it is a closed topic from the technical and experimental. So of course I will cover the whole thing, and actually we cover first of all physics using the slides. Then I will cover a little bit the experiment, and we'll use also other slides to cover existing experiments. So this is a relatively recent talk I gave, so it should be close to be up to date. So what is the idea behind the research of neutrino double decay? First of all, neutrino double decay is the decay of the nucleus, in which the charge is changed by 2 units. And this can happen in essentially 2 ways. One is with the neutrinos and the other one is without neutrinos. It is interesting to note that the very first discussion of neutrinos decay was made by Majorana and Raka in the late 30s. But the first discussion of the 2 neutrino decay, so the double beta decay properly said, is even earlier, Maria Goppermeyer in 35. And it is from her work that it was clear from the beginning that being a second order weak interaction effect, the lifetime of the nuclei decaying to even 2 neutrino beta decay is very long, at least 10 to the 20 years. Today we know that 2 neutrino double beta decay of many nuclei, and the range is that 10 to the 20, 10 to the 21 years, 10 to the 19 for some nuclei. The neutrino-less double beta decay, usually indicated as 0 beta beta, was first discussed by Furri in 39. So it's very old physics. Of course, beta decay was known from the early years of the century, but the theory of beta decay, as you know, is due to Fermi and is of 1932. And of course, with the Fermi theory, it was possible to study second order effect of Fermi theory, and so discuss double beta decay, both with or without neutrinos. At that time, it was not obvious at all that there was a lepton number conservation issue. In the standard model, lepton number is conserved, so you don't expect 0 neutrino double beta decay in the standard model, which makes the search for neutrino double beta decay even more interesting, as we will see in a moment. But at that time, the fact that you should have or not have neutrinos was not obvious, because without electron number conservation, the decay into 2 electrons is perfectly possible. Never think that what is obvious today was obvious 100 years ago. It was never the case. People did not know. So historically, 3 main processes have been discussed. first is the two neutrino double beta decay is allowed by the standard model. It's just a second order effect in which you have the instantaneous decay of two neutrons. This is very inappropriate because it's not a matter of being instantaneous, but the fact is that the nucleus cannot decay in one. If normal beta decay is allowed, of course, you never observe two neutrino decay because the lifetime is 10 orders of magnitude smaller. But if for some kinematical reason that we will see in a moment the normal beta decay is not allowed, then you could have the double beta in some cases. Process number 2 has never been observed. It is exceedingly interesting for reasons that we will discuss. It's very, very important to observe neutrino double beta decay because it is the only known way to prove that neutrino is a Majorana particle, if it is a Majorana particle. Most theoreticians believe it should be a Majorana particle. It would be very surprising, a Dirac neutrino, but we don't know, so we will see. There is a third option, which is not less fashionable today. It used to be more fashionable 15, 20 years ago. One possibility is that lepton number conservation is spontaneously broken in the standard model. And if that would be the case, you would observe a Goldstone boson, which is normally called a Majoron. So if you assume that lepton number conservation is broken by some spontaneous mechanism, the Goldstone boson that you would in general ground expect from the breaking of this symmetry is called the iron, and in this case the two neutrino disappear, but you have two electrons and a iron. As I told you, this is less interesting today. It's very unlikely. Current theoretical bias, because it's not excluded, but there are less and less papers discussing about spontaneous breaking of lepton number symmetry and the Majoran effect. Also because we do know that lepton number is broken by the standard model. I am not a theoretician, I don't want to cover that in detail, but it is not actually true that the standard model conserves lepton number. Non-local and non-perturbative effect of the SCO2 symmetry, the equivalent of instanton in the SCO2 group are called spaleron. They've been studied by Toft in the early 70s. And Toft have proven that this spaleron effect break the lepton number in standard model, but do it in a super small way. So lepton number is not exactly conserved in the standard model, but to any experimental effect it is, because the spaleron effect is super small. But this makes the spontaneous broken of lepton number less attractive, so Majoran theories are rare. I said about Majorana and Dirac. I go quickly on this because I assume you know. If you don't, you tell me. But being the neutrino a neutral particle, by definition, it's not a neutrino because it's neutral, you don't have a unique way to put a mass term. If you want a charge to be conserved, which means if you want to conserve current in the fermion theory, the only mass term you can allow is that one, which is called the Dirac mass term, which is the mass term that is normally written for electrons and quarks in the standard model. And there are no other ways. I mean, if you put a different mass term, you cannot have the Dirac equation for the free particle, and if you don't have the Dirac equation for the free particle, you don't have the conserved charge. But if the particle is neutral, so you don't enforce the conservation of the current, you have another possibility that was discovered by Majorana very early. Immediately after the publication of the Dirac theory, Majorana pointed out that if you don't ask charge conservation, you can write a different term, which is normally identified as Majorana term. Majorana term does not conserve charge. You can see it because you have this charge propagation in the fields, so clearly that field has no conserved charge. And if the neutrino is a Majorana particle, at the lowest level, you can have this diagram in which the lepton number disappears as a conserved quantity. That mass term clearly violates lepton number. Okay? Clearly violates lepton number, and so you can have a Majorana neutrino emitted in one vertex, absorbed in the other one, and in the final state have only the two electrons. This you cannot do in the standard model with massless neutrinos. If you have massless neutrinos, the conservation of helicity at the vertex forbids this diagram, because the helicity of these two vertices must be opposite. And in order for the helicity to split, you need the two things. You need the lepton number not to be conserved, otherwise that diagram is not possible. And you need the mass, because only mass in the particle can change the helicity during propagation. So, in order to observe neutrino-less double beta decay, you need the two conditions. The neutrino must be a Majorana particle, and the neutrino must be massive. By the way, if the mass is zero, Majorana description is equivalent to Weyl description, so there is no physical observable that can tell you if the neutrino is a Majorana or a Weyl spin. Because if it is massless, they are unitary equivalent. But if you have a mass, the two descriptions of the neutrinos are intrinsically different. The two particles are not the same. The properties of the mass term induce physical observable effects. Not many. Neutrino-less double beta decay is one of the few. And it is the only one that can be observed, because you could imagine experiments in which you make neutrino beams and collisions in which this would be relevant, but they are experimentally simply impossible. The only known observable that could in principle be seen in a real experiment that distinguish Dirac and Majorana terms are neutrino-less double beta. You can see neutrino-less double beta decay by, in principle, several observables. The main one is this one, the kinematic one. If a nuclei can decay in a neutrino-less mode, the two electrons in the final state has essentially a well-defined energy, because the nucleus is very heavy. So the two electrons take away all the energy. The recoil of the nucleus is essentially negligible. So, kinematically, a heavy nucleus decaying in another heavy nucleus plus two electrons is essentially a two-body decay. All the energy goes to the two electrons. And so, if you measure the energy of the two expect at some point that when you include the detector resolution becomes a peak of some width that is at the end of the spectrum that is made by the two neutrino beta-beta decay that happens anyway. Because of course the standard model decay with the two neutrinos is always there. And then you have the peak. Or the picture that you have there is very nice, but it's absolutely false because the two neutrino peak is enormously bigger than what you can see in this picture compared to this one. A more realistic scenario is this one. And so, one crucial feature of the neutrino stable beta decay experiments is the energy resolution. The better is the energy resolution, the better is your separation between the zero neutrino peak and the two neutrino broad spectrum. In principle, you would have other observables. For example, in models in which you have right-handed currents, which you expect coupling of these Majorana neutrinos with the standard model, you could have effects of different distribution of the two electrons, angular distribution. This signature can be obtained only in detectors that measure the track of the two electrons. There is one important example, which is the NEMO supernemo detectors, in which the tracks of the electrons is reconstructed in a properly designed PVC. But many double beta decay experiments are purely calorimetric, Warren, Gerda, and other crystal-based experiment. Also, xenon is an experiment in which you don't reconstruct the two tracks in detail. So this angular resolution is not possible for all kinds of detectors. It's possible only for tracking detectors. Another signature of neutrino double beta decay is the fact that the nucleus could not be in the fundamental level. Neutrino double beta decay, of course, you have the nuclei, your nucleus that decay. You have a nucleus with ion zeta electrons that decays theta plus 2, Q plus 2 electrons. And this nucleus could be an excited state of this nucleus, and then you have a decay with 1 or 2 or 3 gammas. This is interesting because you could have a coincidence between the two electron signal and the gamma signal if this decay has a lifetime that can be measured. So it's a signature in which you can extract additional information. There is one experiment that dreams to find the final dollar, which is the EXO experiment that in principle aims at finding the bio atom produced by the decay of xenon 136. But this has never been proved to work. It's a conceptual idea, but never been proved to be really feasible, because you need to be able to identify a single atom of value in a xenon vessel. In principle, it's dreamed via laser, firing a laser and looking at the transition of this value atom, and then you have to detect a single photon emitted by that single atom, and okay, in principle, but never been proved to work. Relevance of neutrinoless double beta decay is huge. I think there is a quite unanimous opinion in the high energy or low energy or astroparticle physics community that the discovery of neutrinoless double beta decay is the most important thing we could do now. Of course, you can dream of very exotic discoveries at LHC or with some non-standard model process. But neutrinoless double beta decay is something that we expect should be there, because we know neutrinos have a mass, and we have strong theoretical arguments that claim, that make the possibility that neutrino mass is Majorana mass a very reasonable one. So you do expect neutrinoless double beta decay, and if you do discover neutrinoless double beta decay, of course you learn something very important about neutrinos. If we discover neutrinoless double beta decay, we would discover electron number violation, which is very important because one of the mysteries of nature today is the fact that the universe is made of matter and not of antimatter. According to standard model, we don't know why. Standard model is almost exactly symmetric between matter and antimatter. CP violation exists, but it's very small. And the amount of CP violation that is in the standard model is way too small, way insufficient to explain why during the Big Bang antimatter has disappeared. So there must be another large mechanism of CP violation, and it might well be, it is a very concrete possibility that this large CP violation effect is in the lepton sector and not in the quark sector. We do know CP violation in the quark sector, but we know it's small. So there are two possibilities essentially. Either CP violation is in the lepton sector and it's large, sufficient to explain, or maybe, of course, there could be a grand unification, or whatever you want to call it, a high energy theory for which the standard model is only an effective low energy approximation, and assume that this very large CP violation is at very high energy. This is also a very reasonable possibility, but investigating if CP violation is in the lepton sector is, of course, the most interesting thing we can do now. Majorana particles would explain in a quite elegant and simple way why neutrinos are so light. This is called the seesaw mechanism, which can be implemented in many different ways, but the key point is this one. If the neutrino is a left-handed Majorana particle, you expect you have a left-handed massive particle, okay? Which means that there exists a particle in which, if you have another right-handed neutrino, and you start with a random matrix, this zero is necessary because this is due to gauge theory. The term with the mu c left and nu left is forbidden by gauge symmetry of the standard model, because you have an SU2 left symmetry in the standard model. So you cannot allow anything in that position. It must be zero. The other are arbitrary parameters, and you must have a symmetric matrix, so that is the most general matrix. When you diagonalize, you get one eigenvalue that is essentially the large value, the M, which you assume to be at the grand unification scale, 10 to the something GeV. You don't know something, maybe 12, 13, 15, who knows. Theoreticians say 10 to the 15, 10 to the 16, but never trust the theoretician. So we don't know. Essentially, we don't know. And you put it in the standard model scale, 200 GeV or whatever, the one you choose. But you immediately get that the other eigenvalue is very small. If you put, quote, a reasonable number, let's say 10 to the 15 for the grand unification scale, and you put a standard model mass, let's say 100 GeV, 10 to the 4 divided 10 to the 15 makes 10 to the 11 GeV, which means 10 millielectron-volt. Beautiful number. Neutrino oscillations say that the delta and square are either 50 or a few millielectron-volts. Solar scale, atmospheric scale. I'm not covering solar neutrinos or atmospheric neutrinos, but if you want, I can. It depends. You will follow the course of Decay and Nathanelli. Who will do it?
Me.
So you will hear about neutrinos from them. You are not following any other neutrino course, so maybe we should say something about neutrinos, but not now. I assume that you know that neutrino oscillation give us the delta and square of the two neutrinos. We don't know the absolute scale, but we know the difference. But you get a very beautiful, this is quite convincing. Of course, I'm joking about the theoretician, but this argument is quite interesting. It's not something you can discard. Because this number is not a random number. All evidence, all theoretical evidence say that if you want to unify the forces, strong, electromagnetic, and weak, and you run the constants using renormalization group equations, using what we know about quantum field theory and about the value of the coupling constants of the three known forces, you end up somewhere around 10 to the 15. It can be 10 to the 14 or 10 to the 16, depending on the details, but that is the scale. And the 100 GeV, we know it's true. I mean, the standard model is a theory of particles at a scale of the order of 100 GeV, which is the mass of the gauge bosons, of the Higgs particle, and of many of the quarks. Some quarks are much lighter, electron is much lighter. We have no idea why. So there is, we have a very poor understanding of masses. We have zero understanding of masses. We don't know why the masses of the charged particle is what it is. We know that neutrinos are much lighter, and this argument tells us that, well, there is at least a reasonable argument that could say why neutrinos are different from the charged particle. Neutrinos are lighter because, differently from the charged particle, you have a Dirac mass, so it's the origin of the mass of the charged particle is probably completely different from the origin of the neutrino mass, or at least could be very different. Never forget that we know nothing about particle masses. Particle masses in the standard model are completely arbitrary parameters, are related to Yukawa couplings, which are completely random numbers that we have to fix with experimental measurement. And the theory tells us nothing about the mass. If you want to look for neutrino and double beta decay, you have to choose one nucleus. In principle, you could choose any nucleus, but it's not true. You end up with a reasonably small number of candidates for the following reasons that I'm going to explain. First of all, you want to measure this decay rate. This decay rate is a lifetime, it's the inverse of a lifetime, and very generally speaking, you have three factors. One factor is a purely kinematical one, which is called the phase space, the blue one. You have a purely nuclear factor, which is the matrix element between this state and this state. The starting nucleus and the ending nucleus. Ruslan will teach us a lot of things about this. He will teach us that it's not completely obvious to split these two factors in the sense that you have to be careful. There are many mistakes in the literature because your definition of the matrix element depends on the assumption you make on the way you compute the phase space. But this is very technical. Let's assume that at least one theoretician knows how to do it right. But there is a recent paper from Iacchello, who is a kind of a guru of nuclear physics, that found a lot of wrong papers around. And then there is a factor that is what contains the physics you want to look at. The blue is kinematics. The orange is nuclear physics, something we don't know. Or well, actually we know very well, but we don't know how to compute well, because it's too difficult. Or at least proved to be very difficult. That matrix element is poorly known, which is a problem, which is a severe problem of this kind of physics. The theoretician should do something. I'm serious on that. I mean, there is it would be enormously important that somebody finds a way to narrow the error bar on the theoretical calculation of the nuclear matrix element. And then there is this function that is due, depends on neutrino masses and on X-enables. It's not just the electron-neutrino mass, okay? Because the electron-neutrino mass is not a defined object, okay? Neutrino are mixing. The eigenstate of mass are not the eigenstate of flavor. This is important to remember. That function depends on the model you choose for the neutrinos. The standard model with Majorana neutrinos, it has a very well-defined shape form that is called the effective electron neutrino mass, which we will see in a moment. But if you put, for example, Majoran decay or other physics in the extension of the standard model, this will bring that function, okay? Depending on which physics you put in, you get a different function. What is the dream candidate? Well, you don't want to have a beta decay around, of course. The nucleus should not decay beta, because if it decays beta, you get the rate of single beta decay will be 10, 11 orders of magnitude smaller or bigger, and you will be killed by beta decays. So it's either forbidden. One possibility is that the mass of Nz is smaller than mass of Nz1, so it is energetically not possible to go beta, but Nz is more than Nz plus 2 plus 2 electron masses. Okay? This is your ideal candidate. Many nuclei fulfill this condition. They are even nuclei, in which this happens for nuclear physics effect, because being even the shell are filled, and when you add one, the mass goes up a lot because you are not filling the shell well. When you add a 2, you go back to the right condition. So it's an exchange effect of nuclear physics that gives you this nice hierarchy of the masses for even nuclei. We will see some candidates. You want Q the end point to be large. The phase space goes up as a fifth power of the end point. So of course you want Q to be as large as possible, which means that the mass difference between the NZ nuclei and the NZ plus 2 must be as large as possible. You want a lot of the phase space, so that you can measure the rate. You want a favorable matrix element, and this is the more tricky thing, because to know that a matrix element is favorable, you must be able to compute it, and the theoretical estimation of this matrix element is very uncertain. And even more important, you would like the matrix element to be easy to compute. It's not the same. The difficulty to compute the matrix element depends on the nucleus. This is pure number physics, but it's much easier to compute the matrix element in which most of the shell are completely full and just a few nucleons are out of the shell. Ruslan can confirm this, but more complex is the nucleus with a lot of nucleons out of the shell, and more difficult is to estimate the wave function and the transition operator and to do the calculation. So the nucleons are not the same. Some nuclei are easy to compute, relatively easy. Some nuclei are much more difficult. And so you have some possibility. And then this nucleus must exist. So not only exist but be reasonable, usable, which means a high isotopic abundance. Otherwise, you have to go through isotopic enrichment, which is a difficult and very expensive thing to do. You can enrich isotopically one material, but if you needed many kilograms or even tons of this material, isotopic enrichment can be extremely expensive if you are lucky, unacceptably expensive in most cases. So it is a showstopper. To get 1 ton of isotopically enriched material, it is maybe possible, for example, with xenon because it's a gas. It's super expensive with the germanium, 100 million euros or something like that. Some material is just impossible. You will never get a ton of neodymium 150 or calcium 40. They are way too difficult to enrich. Xenon 136 is okay because it's a gas. You can enrich in centrifuges without many troubles. Germanium is more difficult but still feasible, but the cost ends up at that level. The next generation germanium experiment aims at 1 ton of crystal, and the expected cost is 100 million just for the germanium, just for the crystals. While for xenon, you end up maybe with 10 million, 15 million, so it's a little bit more affordable. Impossible, or billions if you wanted the calcium 40 or neodymium 150, because the techniques that exist allow only the enrichment of milligrams, very small amount. For example, neodymium can be enriched, but the only very effective technique uses laser beams. So you can enrich only the material you can keep between 2 beams of lasers. So every time you enrich maybe a microgram of material, and if you want to reach ton, it will take forever. You cannot do it. So you have a lot of practical problems that you have to face. Neutrino mass. So that function, F, in case of the standard model, is that thing. Is the so-called effective neutrino mass, and it is the modulus of the sum of the square of the matrix element UEI and I. Okay? UEI squared and I. UEI are complex numbers because in principle you have a phase. And you have CP violation. So that modulus, of course, is a positive number, but you could have interference and cancellation. So depending on the phase of the CP violating phase in the electron sector, which is unknown, you could have cancellations or effects. So you cannot say what is ME at all. You cannot say even if you knew the MI, which you don't, because you know the difference between the different MIs, but you don't know the absolute scale. But anyway, even if you knew the MI, you still lack the phase. So ME is actually a way to measure a quantity that depends on the masses and on the CP violating phase. This is, if you put a Majorana mass term, you also have the Majorana phases. I did not cover neutrino mass, but I hope you know what are the Majorana phases. Do you know? Did you see? No? You know CKM matrix. CKM matrix has only one phase because quarks are charged. And you can only have one phase. But if you put Majorana mass term, there is a node, you have the possibility to have three phases, not only one. So the two additional phases are called Majorana phases. So CP violation in the complex, we will see that. I will cover a little bit of neutrino in one of the next lectures. But now we take it this for granted. These are examples of the calculation of the phase space for different nuclei and nuclear matrix elements. The phase space are not at all similar. You have a very good phase space for neodymium, very bad phase space for germanium, and you are in between for other nuclei. There is an interesting fact, which is a conservation of trouble, which is just by chance, but it's true. You will see in a moment that essentially there is no nuclei that is definitely better than the others, because what is good on something is bad on the other. For example, germanium is beautiful because you can make very good energy resolution, because you can make a germanium diodes, but the phase space is small. Tellurium and xenon, you can make good detector, not as good as germanium, but you can make good detectors, but the phase space is a little better. Neodymium has a beautiful phase space, but it's impossible to enrich, and it's not easy to make neodymium detectors. So whatever you do, you have some problem. There is no ideal nucleus. The best candidate around are germanium 76, tellurium 130, xenon 136. These are the two nuclei that are used most. Gerda and the Majorana use germanium, Quore use tellurium, Exo use xenon 136, Kamlanzen uses xenon 136, Snowplus will use tellurium. So many of the existing experiments that are looking or will look for neutrino stratigraphic decay use these nuclei. Other interesting experiments are looking at the possibility to use other nucleus. For example, another experiment in Grassasso is planning to use molybdenum 100. And other experiments try to use calcium, but calcium, for example, calcium 48, in principle is a good nuclei with a very good liquid value, but the problem with calcium is that it's very low natural abundance, and being a light nucleus, it's very difficult to enrich. So problems are everywhere. The nuclear matrix element is the difficult part of this business, because as you can see, there are many theoretical predictions, and they are in very large and significant disagreement between each other. This is also a little bit of criticism I do with the community of the theoretician, because they don't understand errors, and so they don't never quote errors correctly, because if you can see, for example, the red and the green points, these are the errors quoted by the theoretician. Unfortunately, they totally disagree with each other. So, of course, if you speak to the green guy, they will just tell you that the red one is an idiot, which is not a good explanation. But then you go to the red guy and he tells you that, of course, the green one is a well-known idiot as well. So you have a problem. Sometimes they quote error bars, and in this case they are more credible, and they usually quote large error bars because they have large errors, because these calculations are difficult, they have to do assumption and approximation, and of course that calculation is affected by some uncertainty, which is not easy to estimate. Of course, I tend to joke about the prediction, not being one of them, but of course it's more difficult to make an estimate of a theoretical error than an experimental error. When you do an approximation, sometimes you can put a mathematical bound and say my error is less than, but it's not always easy. Sometimes you make an approximation, but you don't know exactly how well you are doing here, how well you approximate the true one. So sometimes it's not easy for the theoretician to quote an error, but in this case they just don't quote it. And so you don't know what to do. Because if you have a number without an error, it's not easy to make a statement about the reliability of the calculation. This is what is the scenario for neutrino masses. Neutrino oscillations tell us two things. Particularly, they tell us the two mass splittings. We know that there is one small splitting, which is normally called the solar mass splitting because it was measured for the first time studying solar neutrinos. But then there is another splitting that was measured for the first time analyzing atmospheric neutrino that is called the atmospheric splitting. The two numbers are well known, and we now know that one is the difference between a neutrino that is mostly electron neutrino and what is mostly a muon neutrino. But as you can see, it's not very correct in the sense that M1 is dominated by electron neutrino. M2 is a quite democratic mixture of the three flavors, while M3 is a quite democratic mixture of tau and mu neutrino with a small amount of electron type. But we don't know the order because the two delta n square are measured in modules. Oscillations are not sensitive at first order to the sign of delta n square. In order to be sensitive to the sign of delta n square, you have to look at second order effects in the three neutrino oscillations. There will be some experiment, like for example Juno or Orca or Bingo, that will try to measure what is called the neutrino mass hierarchy. So if the order is the one on the right or the one on the left, but current data cannot distinguish between the two. This is very relevant for neutrino double beta decay, because if the hierarchy is so-called direct, 1, 2, 3, it means that the electron neutrino is the lighter one, and so it could be very, very light. It could be 1 milli electron volt or even more, or even less. And if the electron neutrino is 1 millielectron volt or even less, the rate of neutrino-less double beta decay will be impossible to measure for this generation, next generation, and probably next to next generation. Because to reach the direct hierarchy, it will take at least 100-ton detector. And nobody knows at this point in time how to make a 100-ton detector at an acceptable cost and with a reliable approach. It's not for today and not even for tomorrow. It's at least the day after tomorrow. But nobody says that this is the right one. We could have this one. I recall you that quarks are not in the right order. There is a mixing because U is lighter than D, but S is lighter than charm. Okay, so there is no real reason why the masses should be left or right. No good reason. We have no understanding of the masses, so we have no reason to believe that left is better than right. We call it direct, and I'm directed, but it's a random number. Okay, it means nothing. There is no real reasons to believe that the masses should be in the same order as the flavors. Okay? So, if it is left, we are dead. If it is right, we have a hope because we know this split. This is 3 10 to the minus 3. The square root of 3 10 to the minus 3 is a few 10 to the minus 2. And the next generation experiment will reach sensitivity of a few 10 to the minus 2. So, within 10 or 20 years, we might discover double beta if nature has chosen the right order. We will not discover double beta very soon if nature has chosen the other possibility. In the slide you see also limits from cosmology. They are still far, so we are still in good shape. And I predict, if I'm wrong, it doesn't matter, but I predict that cosmology will measure neutrino mass before terrestrial experiments. Because I think that next generation cosmological surveyors like Euclid will have sensitivity at the order of a few millielectron volts, and so I suspect that they will give evidence on neutrino masses from cosmological observation. Of course, it will be not a totally convincing measurement because it will be the total mass of the 3 neutrinos. They will not be able to separate. But they will give, I suspect they will give the scale of neutrino mass before double beta decay experiment will reach that sensitivity. We have to be very lucky to discover neutrino mass already with Quore or with Gerda 2 or with this generation of experiment. We have to be quite lucky. While next generation, Quore 2, Quore New, or Majorana, or Nexo, or Next, or many dream experiments of the decade between 220 and 230, that could do the job. But probably cosmology will arrive first. Oh, okay. It doesn't matter. But just to give you a feeling that there is this, there are two possibilities: to extract neutrino mass from direct experiments and to extract neutrino mass from cosmological data. And it's very likely, in my opinion, that cosmology will arrive first, unless neutrino is super light. Okay, neutrino is 1 millielectron volt. Probably nor cosmology nor detector experiments will be able to give a number. But if neutrino is not super light, cosmology can. Which nuclei? 10
abbiamo detto 5 e mezzo, ci siamo quasi? Maybe. Okay. These 2 slides and then it's a good point to stop.
I told you what is the typical reason why you choose a nucleus. The kinematical one is perfect. If you take a nucleus like, for example, xenon 136, it's an even nuclei. Even means A is even and Z is even. Okay? Both even. If you remember nuclear physics, you know that there is these terms of pairing of nucleons. So when it's even, you have more binding energy and the mass is lower. And so it happens that, for example, what happens for xenon 136, that xenon 136 is lighter both than cesium 136 and iodine 136. So it cannot beta decay or beta plus decay with any of them, because kinematically that transition is forbidden. But with 2 more nucleons, the binding is even more. And barium 136 is even lighter than xenon 136. So you can kinematically double beta to barium. This is the prototype. Most of the neutrino double beta decay candidates are even nuclear like that, in that condition. That there is a nuclei that is at the bottom of a valley of the same A, 136. The minimum, 56 is even, 136 is even. And this minimum mass makes this as a candidate for beta-beta. And 136 cerium, a candidate for beta plus, beta plus. But beta plus is not easy to detect, so you usually search for 136. Very good. The candidates that are good are that one. These are the nuclei that are used around. You have the Q value and this isotopic abundance. When I said there is a conservation of trouble, you can see that there is a kind of a correlation. When this is big, this is small. Okay? It's not completely true, but there is none of the big Q has a very big abundance. Okay? Because the best Q is calcium, that is almost very poor. Neodymium is also very high in Q value, but the abundance is only 5.6. While, for example, if you look at very high abundance like tellurium, yes, but the Q value is not that good, 2.5. And also, others have not very huge abundance. Tellurium is good because of the very high abundance, so using natural tellurium is a good choice, but you don't have a very beautiful Q value. So you need a very good detector, because in that region, as we will see, radioactivity background is not zero. So either you make a very good energy resolution detector or you have troubles. That's why volumetric technique is crucial, because they give you the nice energy resolution that you need. Another beautiful option from the experimental point of view is germanium, because you can make beautiful diodes, and so you can make very well-known detector with very well-known technology, which is the semiconductor technology. So from the technological point of view, germanium is beautiful, but the Q value is not perfect and the abundance is not very high. So you have to do enriched germanium, which is very expensive. And again, you have to be very careful with the radioactivity, because in the 2 MeV region, potentially you could have a background if you don't do things right. If you do it right, you can control this background and do it with an experiment, like what the Gerda is doing, or Majorana With calcium, if you could make a calcium experiment, you could essentially ignore radioactivity, because all radioactivity is below 2.615. What is 2.615 is the thallium-208 line, which is the highest energy line in the radioactivity spectrum. So below 2.6 ixompleones, you have radioactivity. You have to fight against radioactivity. Above 2.6, you are in an easy place. You still have the alphas, but the alphas are easier to fight. But you don't have gamma lines due to natural radioactivity with energy much above 2.6. But the nuclei with 2.6 are not very easy. One possibility is molybdenum 100, and there is a plan to use molybdenum because molybdenum could be very promising. It's above the 2.6, so it's in a place in which radioactivity backup can be low. And if you find a way to make a good molybdenum polymer, you are in a good shape. This is an option for the future. Nowadays, current experiments use germanium, xenon, and tellurium, essentially, with many R&D projects on the nuclear. Last slide is this one, in which you have what I told you, the conservation of sound, because the isotopic abundance is very stable. You have the calcium, which is very bad in isotopic abundance and happens to be the best one for the value. Neodymium is the second worst here and is the second best here. And these are flat and these are the region. You understand why tellurium and germanium and xenon are the ones that are used most. It's also a technological issue and availability issue and a purificability issue. You need a very pure material. Some materials are easy to purify. Some materials are impossible to purify. Some materials have a radioactive isotope. In this case, you have troubles. So finally, you end up that xenon, tellurium, and germanium are